Hi everybody, we're going to be covering section 5.1, page 3, and it's going to ask us to connect the features of the graph to the derivative. So on page 1 of this section, we were looking for all the critical points and max and mins given a graph. And then on page 2, we were trying to find the critical points only given the equation, so not the graph. And our ultimate goal is to be able to find the max and mins without the graph. And this page is going to help us find some characteristics of graphs and their derivatives to help us be able to do that. So to help us just use equations to find max and mins. So this first example has us look at a graph g of x, and it wants us to focus at the point x is equal to -2. We notice that there is a relative max there because at -2, the y value is higher than the points around it. All right, so then it wants us to look at both sides of our max. So on the left-hand side of our maximum, if we draw a little line kind of following the curve, we see that the graph is increasing. It's going up from left to right. And then what's the derivative doing there? So if we remember, the derivative is the slope of the tangent line. So if we are increasing, going up from left to right, our slope or our derivative is going to be positive. Now let's look to the other side of our critical point. So the right side, we're going to be going down. So again, we're still moving from left to right. So we're going to start at our max and then go further to the right. And we see we're decreasing, we're going down. And again, the derivative is the slope. So if we're going down, we're going to have a negative slope or negative derivative. So really meshing the idea that the slope of the tangent line is the derivative is going to help us here. So as a recap, we went up, then we went down, and that gave us a maximum. We changed directions from up to down, and that gave us a maximum. All right, so on this next portion, it's asking us to look at the x value 2. So at the x value 2, we see that we have a relative minimum because it is lower than the points around it. Okay, so now let's look to the left of our relative minimum, still going from left to right. So on the left-hand side, we're going down. So we are decreasing. And again, we want to emphasize that the derivative is the slope of the tangent line. So when we're asked to find the derivative, if it's positive, then the graph is increasing. If it's negative, the graph is decreasing. Since the graph is decreasing here, we can say that our derivative or our slope is going to be negative. Now to the right of our minimum, we are going back up. So we know that our original function is increasing. And if we look at our derivative, that's the slope. Since we are increasing, the slope is going to be positive. So a recap, we went down, then we went up. So we still changed directions, but the order matters. This time we went down first, then up, and that gave us a minimum value. And here we have it. This is the moment we've all been waiting for. I don't know about you, but I'm super stoked. This is the first derivative test for Extrema. This is amazing, and we're going to fully utilize this the rest of class. So yeah, we're going to learn to love this. Suppose that C is a critical point for our continuous function f of x, and that its derivative is defined for values around that critical point as well. So we have our critical point at C, and we're going to look at the tendencies to the both left and right of our critical value C. So part 1 is talking about having a positive derivative to the left of our critical point. So let's graph our critical point, kind of like a chart. And then on the left-hand side of our critical point, we're told that the derivative is positive. So if the derivative or slope is positive, that tells us the original function is increasing. Then it also tells us that the derivative is negative to the right of our critical value. So on the right-hand side of our critical value, we have a negative derivative, which tells us that our original function is decreasing. Because if the slope is negative, we're decreasing. And hey, we changed directions. We were going up, then we went down, so we had a maximum value there. You can think of a roller coaster if you're going up, and then you hit your peak, and then you go down. You hit a maximum. All right, our next part, we still have our critical value C, and now our derivative is negative to the left of our critical value. So let's graph our critical value, and we have negative on the left. So f prime being negative tells us that our original function is decreasing, because again, the slope is negative. Now on the right-hand side of C, our critical point, the derivative is positive, which tells us that the original function is increasing. All right, so we changed direction at our critical point. We went down, then up. So we have a minimum value there at our critical point. So for both part 1 and 2, we changed direction going up to down or down to up. So the order matters to determine if it's a max or min. We went up to down to be a max, and then down to up, and we got a minimum. Now, what happens if we don't change directions? So what happens if we have the same sign on both sides of our critical value? So let's check it out. If we have a critical point, C, and on the left-hand side we're going up, and on the right-hand side we're going up. We didn't change directions. It doesn't look like a max or a min based on our arrows. And again, if we have our critical point, and on the left-hand side we're going down, and on the right-hand side we're going down, it didn't change directions. We don't have a max or a min at our critical point. So neither a max nor min. Now that looks great just with arrows, but even better, let's see an example that we're used to. So x cubed gives us a nice little visual. You can see that we have a stationary point at 0, 0, because that's where the tangent line would be flat. So we have a critical point there. Now if we go from left to right, we are increasing, we hit our critical point, and we're increasing again. We don't have a max or a min at C, because that critical point is not higher than all the points around it, and it's also not lower than all the points around it. So that's what it would look like with a real curve. Now this example is important because it gives us the idea that not all critical points are max or mins. So even though we have a critical point, it's not necessarily a max or a min.